is true by definition. For the right-hand side, we, I don't want to use the word partition, so we split up the number of possibilities into cases. And the cases are based on, in the original partition, on the left, the number of piles with at least I puppies. If, and so now I'm going to be bold and do the general case. If I have n puppies, k piles, and suppose that, to do the general case, suppose that in that partition there are precisely I piles of happy puppies. Well, if there are I piles of happy puppies, then, oh my god, if there are I piles of happy puppies, then, give me a second, if there are I piles of happy puppies, for each of the ways of dispersing well, if there are I piles of happy puppies, but there have to be a total of k piles, then there are some other piles with just one puppy in them. And so, okay, what I want to say is just kind of add, I'm having trouble finding my words here, but I'm sort of failing, I want to move on. But basically what we do is we take, you see what's happening here. For every one of these numbers you just add 1 to every one of the piles and you end up over here. And so the exact way to write this out, I think I need like time and no pressure to say it precisely. I had it before this video started in my mind. It's something like, oh, here we go. If in the original counting, the thing that we were claiming that both sides count, the number of ways to distribute n objects into k piles, where no pile is empty, if no pile is empty, then there's just always a happy puppy, or there's always a puppy, I should say, not necessarily happy, in every pile. If there's always a puppy in every pile, at least, then consider the case in which we have I piles of happy puppies. Well, if there are I piles of happy puppies, then, but there's always at least one puppy in every pile, then if there are n total puppies and k total piles, then I've already used up k puppies to put one puppy in each pile. So I have n minus k puppies that remain to be dispersed to the piles. But if precisely I of the piles are piles of happy puppies, then now my job becomes dispersing the remaining puppies, the remaining n minus k puppies, into the number of happy piles. That is to say, piles with more than one puppy in it. Okay, there we go. This was the full-on combinatorial proof. I hope you're not watching this whole video. That would be terrible for you. Good. That was so hard, and it was even like a familiar thing that we had already sort of encountered a couple times. Now we get to part B. Part B is a totally different thing. Part B says, and this is what makes this problem so wild, Part B says, I'm going to now introduce a completely separate combinatorial construct called QNK. And once again, I will define it combinatorially. What is QNK? It's the number of partitions of n for which the largest summand is exactly k. So is the number of partitions of n for which the largest summand is exactly k. Okay, and now there is a claim that is made about this Q thing, and the claim quite shockingly, is that QNK is the sum from I equals 0 to k of Qn minus k I and with base conditions Qn1 equals 1 and that Qnk equals 0 for k greater than n. One will note that this formula is the precise formula on the left with the same precise base conditions. And so, what we are going to conclude in part C is that in fact Pnk and Qnk are precisely equivalent. Here we've defined Pnk as the number of partitions of n objects into k piles, or with k summands. Here we are defining a new thing called Qnk, where it's the number of partitions of n for which the largest summand is exactly k. In other words, it's the number of ways to put n puppies into piles where the largest puppy pile is k. Okay. Well, first let's prove this. Let's prove this rule. And how do we prove this rule? Well, before we can prove it in general, it might be a good idea to try it with some numbers. So once again, I'm gonna get some numbers here. So I'll just take Q83. Why not? According to this formula that we're supposed to prove, what should Q83 be? Well, once again, here I'm not even being told that Q. Well, it's just stupid to start with 0, I guess is what I want to say. If we take this definition combinatorially, then of course I can't make partitions in which the largest summand is 0. That's just not even allowed. So I propose that once again we just start with 1 because anything 0 is going to be 0. Okay, so Q83 is then, according to this formula, well, it's just the exact same thing, right? It's Q51 plus Q52 plus Q53. Okay, and well, let's go here. What is this? Let's just play around with these for a minute. What is Q83? Q83 is all the ways of splitting up 8 in which the largest pile is of size 3. Okay, well, if the largest pile is of size 3, then I guess we could do, yeah. So then there's at least 3, and now it's like, I guess I could do like 3 plus 3 plus 2. Yeah, that's 8. Or I could do 3 plus 3 plus 1 plus 1. That's also 8. Or I could do 3 plus, well, they're all going to start with 3, because that's the definition of this. The largest pile is of size 3. So 3 plus, and okay, even already we're sort of feeling what's going on, right? There's just going to be a pile of size 3. So this is just equivalent to all the ways of partitioning 5, I guess. So, well, almost. So 3 plus 2, 3 plus 1 plus 1, let's just keep going. 3 plus 2 plus 2 plus 1, 3 plus 2 plus 1 plus 1 plus 1, and 3 plus 1 plus 1 plus 1 plus 1 plus 1. I think those are the 5. Yeah. Okay. And now, what's Q51? Well, this is the number of ways of splitting 5 up into piles for which the largest pile is of size 1. Well, there's only going to be one of those, right? 1 plus 1 plus 1 plus 1 plus 1. How about Q52? The number of ways of splitting up 5 into piles such that the largest pile is of size 2. Well, there's 2 plus, and now I guess I could do 2 plus 1, or 2 plus 1 plus 1 plus 1. I guess those are my 2 options. Yes, they are. And how about cube 5, 3? Well, this is the way to split up 5 where the largest one is a 3. So I can do 3 plus 1 plus 1. And that means I must have screwed them. Oh no. Or I could do. Must have missed one here. Oh, or I could just do 3 plus 2. Sorry. 5 into 3. Yeah. Okay. So, great. Well, once again, I think this proof is even a little bit easier. Once again, if you look at this, it's impossible to fail to notice. It's impossible to not notice something. Here, let me make it a little bit prettier by fixing this. If we first do this 3 plus 2, oh boy, 1 plus 1. Yeah, teaching is hard. This goes here. This goes here. These two go here. Cha-cha and cha-cha. And in a horrible way of spacing, this one goes here. Okay, and so actually the sort of correspondence between the 5 partitions on the left side and the 5 partitions on the right, I think are even more obvious. You just drop the leading 3. Okay, and now this is just sort of just done, right? That this is true, because of course, if I want to make 8 into piles where the largest pile is of size 3, then every one of those partitions is going to have a pile of size 3 in it. And so having designated that my largest pile will be of size 3 and that there will be a pile of size 3, then obviously I just have 5 puppies left, and what am I going to do with those 5 puppies? Well, I have to put the 5 puppies into piles such that, well, how big can that second largest pile be? It can't be more than 3. And so you could have 2 piles of size 3, but you can't have any pile which is larger than 3. And so Q83 just kind of writes itself. If there has to be a 3, it's just the number of ways of distributing 5 puppies into piles where the largest size can be, where the largest pile can be 3 at most. In other words, either it's 5 puppies into 3 piles where the largest pile is of size 3, or 5 puppies into piles where the largest pile is of size 2, or 5 puppies into piles such that the largest puppy is of size 1. In other words, we are our 3 cases which give rise to this plus are the cases about that consider the size of the second largest pile. That's what I is in this case. I is the size of the second largest pile. And now to do this properly, but just saying it, not writing it, claim both sides count the number of partitions of n for which the largest pile is of size k. Left-hand side, this is true by definition. On the right-hand side, if the largest pile is of size k, and there is a pile of size k, then make that first pile. That leaves you n minus k objects to distribute into piles. And the second largest pile can be at most k. And so how big is that second largest pile? Well, suppose the second largest pile is of size I. If the second largest pile is of size I, then there are this many ways to distribute the remaining objects by the definition of Q, where the largest pile is I. Okay, so this just kind of writes itself, I think, this combinatorial proof. Okay, and sort of shockingly now, Gossett just sort of leaves us without any sort of resolution here, in my opinion. What we have shown in an extremely convoluted manner, I think it's convoluted, or well, students in the past have pointed out to me that this proof is lacking in some way, because while it is perfectly correct that this has this satisfies this formula and and satisfies these base conditions, and this satisfies this formula and these base conditions, and so these are sort of guaranteed to be equal to each other. What I now sort of crave is like a direct argument that Pnk equals Qnk. Why should So PNK. Why should PNK? I'll put a question mark. I don't doubt that it's true, but I don't think I understand why it's true either just right yet. Why should the number of ways of putting n objects into k piles be the same as the number of ways of arranging n objects for which the largest pile is of size k? I feel that we've been left without an intuition on this. Okay, so smart people have told me in the past that I can do this visually with a sort of a diagram. And so let's take the 5 ways of representing PA3 and to put them into a diagram. So there's the 6 plus 1 plus 1 way. There's the, this is going to be a little hard to squeeze in. 5 plus 2 plus 1. 4 plus 3 plus 1. 4 plus 2 plus 2. And 4 plus 3 plus 1. Okay, well here I shall draw this with these little boxes. So 1, 2, 3, 4, 5, 6, and 1, 1. Okay, so you are to interpret this picture as there are 6 objects in the first pile, so thinking of the rows as being piles. 1 object in the second pile, 1 object in the next pile. Okay, and just keep on doing this. 2, 3, 4, 5. Excellent squares I got here. And that's 2, and this is 1, so I think that's clear. Oh my god, why is this so bad? Okay, and 4, 3, 1, so that's 4 in the first pile, 3 in the second pile, 1 in the third pile. 4, 2, 2. 4, 2, 2, and over here, 4, 3, 1. Okay, so, good. Cha, cha, and cha, cha. Okay, and now, what we do is take this thing and rotate it. Or rather, don't rotate it. Perform like a reflection or whatever. Swap rows and columns. Creating new pictures, just sitting on the floor now, creating new pictures. In other words, take this, this 6, 1, 1 diagram can be rewritten as a 6 this way, 1 this way, 1 this way diagram. Whoa. And now, this is the number of ways of splitting 8 into 3 piles of size 6, 1, and 1. But for every one of those ways, by just rotating the diagram, we have now 3 piles. Pile 1, pile 2, pile 3. But now I have 6 piles. And the largest pile is of size 3, then a pile of size 1, 1, 1, 1, 1, which is this one right here, boom, on the bottom. In other words, by just by rotating the figure, we see that if there are only 3 piles, then by either reinterpreting the picture or performing this sort of geometric transformation on it, we now see that the number of piles can be reinterpreted as the size of the largest pile. And over here, 5 plus 2 plus 1, this gets rewritten as, this is embarrassing if I get it wrong, so that's like 5, 3, 4, no, there we go, 5, and 2, and 1, I guess, right, like that. Yeah. And now, again, a pile of size 5, a pile of size 2, a pile of size 1, gets reinterpreted as a pile of size 3, a pile of size 2, 1, 1, 1. And in every one of these cases, because I start with 3 rows, when I perform this reflection, I get a figure whose first row is guaranteed to be the largest and guaranteed to be of size 3. Yeah, and so, okay, I don't really need to do this but I will finish, and then I'm going to stop this video, I think. Cha, and then we get 3, and then 1. Cha, yep. And then over here it's like 3, no, 4, 4, and then it's like this, right? Cha. And then like this. 4, 2, 2, and then like a 3, and then a 1. So this is, like, for example, this was 4 plus 3 plus 1. This is 3 plus 2 plus 2 plus 1. Okay, so this is, now I can erase this question mark, and I have now shown a sort of direct correspondence between the P numbers and the Q numbers. Or rather, what I've done here is, okay, let me just, if I've gone this far, I might as well write this out. What is this? This is 3 plus 1 plus 1. This is 3 plus 2 plus 2 plus 1. This is 3 plus 2 plus 1 plus 1 plus 1. And this is 3 plus 1 plus 1 plus 1 plus 1 plus 1. And what I've now done is I've sort of shown, at least for P83 and Q83, but of course it generalizes, that I've shown a sort of direct correspondence by matching a particular partition. This is what the first row in black is every partition of 8 into 3 piles corresponds precisely to a partition of 8 into piles in which the largest pile is of size 3 by a reinterpretation of the diagram. So that direct one-to-one correspondence between partitions that meet this, partitions of 8 that meet this requirement and partitions of 8 that meet this requirement shows that in fact they count the same thing, or that there are the same number of them. The number of them are the same because every one of these partitions matches precisely with one of these partitions, vice versa. Okay, good. I'm just not going over 25. It's just too much video. Goodbye.